I realize I'm the last speaker, and I have only 75 years to cover. I mean, the past 50 and the next 25. I thought I would have a short talk with only like 60 or 70 slides. But also to make it more comfortable, I mean, I think that a lot of you know most of it. So let me start by thanking the organizer for this great time that we're spending together. And so, of course, the subject started in '65, so therefore about 50 years. I think I will only jump to sort of a few critical steps. And of course, I think the one critical in terms of number is we got a Planck spectrum, and with a very well-defined temperature, and that was out of the first, I mean, it was presented initially in the 90s at the AAS by John Mather, and from that we extracted not only a temperature, but we also extracted upper limits on any deviation of this, like Y and mu, which is essentially controlling how much energy could have been dumped into the microwave background after the thermalization process, as we actually teach to all our students. Now, and this hasn't been revisited since then, mostly. But now we do have a lot of interest because with the progress in terms of instrument and detectors and so on, we can now imagine to go to much higher level of precision. And then we are starting to consider that, for instance, silk damping, which is sort of guaranteeing that there is a conversion of fluctuations in terms of energy input, which you have to dissipate those fluctuations, we can actually dream to actually measure that. And so that sort of suggests that in terms, we might actually be probing this, in particular the mu distortion, might actually be revealing, for instance, that there is a lot more very small scale fluctuation that had to be dissipated at the silk damping time. In other words, we could have a handle over scales which we cannot probe with the CMB directly on very, very small scales. So that's very exciting. On the other end, what is less exciting is, of course, we now start to have a view of, even at the monopole term, since that's what I'm talking about, we have a lot of processes that we have to cope with. And so just imagine, I mean, you have this, monopole term, and you are trying to decipher what all these terms are. Now, there is an actual experiment that has been proposed. It's called Pixie. It gives you the kind of sensitivity that one can hope to achieve in about 4 years. It was actually proposed to NASA in 2016, and we'll get the output of the selection in about a month from now. So it's really contemporary stuff. Now, in my view, this is really sort of a path-breaking, a ground-breaking experiment, because we don't know how far we'll be able to go in terms of dealing with all of these foregrounds. But if we do, then we'll be able to look at really interesting signatures, as I just said, like deviations on scales much smaller, deviation from a featureless power spectrum on scales much smaller than those that one can be probed directly with the CMB. And if you think even further in the future, I mean, you could even think of doing the recombination lines. Okay, now I mentioned Kobe, and that hasn't, but for now, we're still with a FIRUS result. Now, you also know that after a long period where we essentially had just upper limits, the DMR instrument also led us the first detection of the fluctuation part, and in '92, the power spectrum was looking like this. So we had essentially a number, which was the sort of amplitude of the fluctuations. Then the history has been going very fast since then. Oops, yes, of course. Sorry. Very quickly, in '94, we started to have some evidence that there was a bump. And it was not enough to be able to tell whether this was coming, as was pointed out, from strings or from an adiabatic fluctuations, but still, yes. It's also the time where there was 2 events into CMB. Actually, these are very old slides of mine, so I'm actually surprised by some of the animations. So in '96, this is the time where both WMAP and Planck were selected to actually build the next generation satellite after COBE. after about, and for us, we put the Planck, I mean, we started to work and put that proposal immediately in 92. So that was after 3 years of work. So you can immediately see that we've been spending a fair amount of time building the experiment, testing, then flying it, then analyzing it to this very moment. Now let me jump to, well, what is the current situation? And I know that I'm skipping over a lot of very interesting things like the boomerang and maxima result in the 2000 that showed us that we were close to omega equal total and sort of giving credence to the fact that we might be living in an omega equal matter 0.3 universe and still being omega total close to 1. So it's been shown a few times. This thing that came out of the computing center that I actually built at my institution downstairs. And well, I think I don't have to say much, but the value is not so much that it's not only that this is complete, that that the noise level is very small, that this is well matched in terms of full width of max to the silk damping, which is smaller than 5 minutes of arc. But what is really important is a number of cross-checks that we can do to actually give some credence that we actually understand systematics and that this is actually real. So I want to spend a little bit of time on this plot. What you see here is a collection of null tests. And what is done here, let me compute, for instance, what is the temperature power spectrum of the previous map, computed at, well, not actually at the previous map, at one of the frequency map, let's say 143 internal cross correlations. I clean it from foregrounds, and now I take the difference, say from the 100 gigahertz, the same operation. I extract the power spectrum of the CMB with the same foreground model at 100 gigahertz, and I look at the difference. This is a null test. It just says, if I've done my work properly, okay, I've accounted for all the systematics, both instrumental and in foregrounds, I should get the same answer on the sky. When I look at the difference, not only I should have a null test, but I should also have something that is statistically compatible with my description of the noise. That is all the covariance matrix and so on that encompasses all of this. In other words, and this has been expressed now in 1, 2, and 3 sigma units. So now you can even count points to see how many are at the 1 sigma, how many are at the 2 sigma, and so on. Now you can do this. I've just pointed out to 2 of them, but you can do this for any of the sort of core frequencies that we've used to build this. And it's all the time we're getting the same answer all the way down to the statistical level. You can also do some other things. One of the blue is actually what we actually delivered to you as a likelihood to compute parameters and all of that. And that is, for this release, it's based on the cross spectra are based on the time cut in the data. But that's one way of doing it. You can do this differently. You can actually compute the cross correlation by using different detector sets. Okay, that's another way of looking at things, which is completely different. You cross correlate not by cutting things in time, but actually in terms of physical detectors. Well, we also get the same answer. So maybe we're starting to deliver, I mean, we think that we're starting to have really many ways to get at the same result, and we have a sound understanding of the statistics. Okay, well, Planck delivers something else, which is a second full sky map that people have already alluded to, and that it's a CMB, but we've also done, of course, at different frequencies, and I'll get back to this particular one. If we look a little bit more carefully, well, the background, by the way, is the temperature. So you can immediately, and these lines are giving the orientation of the polarization field, so you can immediately see the cross correlation between temperature and polarization. Now, you may have seen I won't this curve, but you may be struck by the fact that you see these sort of curly things, and this is an artifact. In 2015, we haven't brought the data to the point that I showed you in temperature, where we believe that we understand everything. And in particular, large scales, we believe that we have still some systematic residuals. So we thought that there is no point of misleading everybody, so we essentially excise those scales, the very largest scales, and so this is missing the largest scales. And then we had also too smooth on the smaller scales because you don't see anything otherwise. So that picks up the characteristic scale, which is a bit misleading. So I just wanted to warn you. And actually, when you are not doing this smoothing, this is what you see at 5 minutes of arc resolution, which is still with a signal to noise comparable to 1. And so if you compare this gigantic step forward we've done with what was known before, just before we released it, what was known before was about these 50 arrows from WMAP. So we just went from that to that. Precisable increase of information. Another thing that we did first was actually analyze the temperature and the polarization map to actually extract a projected mass map through the lensing effect. Okay, so these are maps. Actually, this is not the way we make contact for most of the cases with physics. So what we do, and most of the information, apart from the fact that we checked for isotropy and homogeneity, and as well as we checked for the amount of Gaussianity, is a two-point statistics, which I remind you is exhaustive for a Gaussian process. This is pretty much the state of the art. So you've got everything in pretty much one slide. So this is a temperature power spectrum, the thing we promised to the agency that if we give us that money, we'll do the final job on this. Well, I think we did deliver. But we did much more. The blue points are also giving you the E-mode power spectrum. These are the phi, that is the gravitational potential on the line of sight, the projected one from us to the last scattering, which is inducing the small weak lensing effect on the map and cross-correlating different scales. You also see the ACT pole, SPT pole results there. It's essentially all the field concentrated there. The only thing that I've excised there is points which have too large error bars, so they cover all the plot without bringing any information. There is also an interesting thing here, which is the bicep result as corrected by Planck, which shows that what you get is the B modes are expected from lensing, and there is no indication that there is anything else in terms of primordial gravitational background. Now, if you look from the purely experimental point of view, Planck has measured about 1.1 million modes with a signal to noise greater than 1 in temperature. About 60,000 in the cross correlation between temperature and E modes, which I'll get to in the next slide. About 100,000 with EE, so you see we are missing another million modes to measure. That's for the next generation. For the B mode, well, we've measured tens. So that's a wide open space for investigation. And then, well, you see the status, I mean, 100, maybe of the order of 100 in terms of modes deduced in terms of the projected gravitational potential. Okay, so that's sort of a, and once you've done that, you've computed the covariance matrices and so on, you embodied this in the likelihood. From the purely experimental side, the job is pretty much done. Of course, we want to extract a little bit of knowledge out of this. So as was pointed out, one of the things, this is the TE spectrum. This is about the size of what would be the horizon if there was no inflation. And then you see this super horizon, quote unquote. I mean, if anti-correlation, it's very hard to understand if there is not an accelerated period of expansion, and that this is actually, it's only the Hubble length that we're plotting here and not the actual horizon. And so we can explain this. And as was pointed out, I mean, that's one of the beautiful things we are getting out in terms of support for the inflation paradigm. Another thing is, well, what about adiabaticity? You do expect fairly different, well, with a different content, you expect quite a different things for the relationship between temperature and polarization. Well, actually, one finds that this is offset by exactly the amount that you expect between the temperature and E mode, which is also pretty strong support of adiabaticity. Next thing is, well, let's focus a little bit at the temperature power spectrum. So these are the error bars, and so they are there. You don't see them, but it's because they are smaller than the size of the symbol. One of the amazing thing, I mean, that is truly amazing to me, is that this is actually very well described by a very simple model. And with all the statistics, and you see that, you know, everything there is well described by this very simple model, which, well, having been around for a long time and knowing the state of cosmology in the 80s, thinking that the kind of ideas that we were developing by then would actually remain and describe everything with that level of precision, I wouldn't have bet a dime on this. Well, still, that's life. Now, the next thing you can do is actually look at the temperature polarization power spectrum, or the E-mode polarization spectrum. And these are the actual data. These are the dots. And the blue points are actually when you bin things per range of L. Now, let's see, that is, if we understand anything about the universe, let's see what the previous fit in temperature tells us. This is a red curve, and these are the residuals. You would agree that this is a pretty good predictor. In other words, the model, describes very well both temperature and polarization. There are residuals, though, and that's we are very careful to warn you. And these are the levels that we expect to be the systematics residuals of the order of 1 µk square. So it means, and we have been very clear, that is, it's enough to check consistency between temperature and polarization. It's not ready for prime time to look at tiny little wiggles in the polarization spectrum as you can with temperature. But still, so I say, well, you can predict temperature from temperature to polarization. You can do something that you may not know, is let's fit directly the lambda CDM class of model to say TE as compared to, you know, the temperature part. Well, first of all, you get the same numbers. That's the part one. But secondly, when you look at that, most of the parameters are actually with similar error bars. That is to say that polarization, even already now at the Planck level, is already with a similar power, constraining power, independently of temperature. That was not completely appreciated. And I think that's, we have really independent probes with similar level of precision nowadays. And what we find, it fits with a single, you know, we have two different views. We are revealing the early universe through two different probes. And this is all consistent with an amazingly simple model. Of course, that allows this also to look for deviations. And one of the examples that is precisely the amount of isocurvature modes, which I just showed you by just the argument that E mode should be phase shift. When you put polarization in, look at the amount of isocurvature modes, in fraction that you can tolerate. So it's, you can reduce this quite a bit. And if you are thinking of taking the broad view of how much we've learned, well, let's say in 2004, the error bars were 6%. In 2015, it's 0.5%. So in this sort of 10-year time scale, we've made an improvement by an order of factor 10. That's pretty fast. That starts looking like Moore's law. Well, let us ask another question. What is the value of NS? Well, you've known, this is 2015, for instance, it's 0.965 plus or minus 0.006. Well, in the Kobe days, we were at the 0.6 level. This is a 100-fold improvement in 20 years. Well, that's not bad. And of course, I don't have to stress in that audience that this was a pretty damn important thing. And, you know, this is one of the things, the iconic predictions of inflation, even though some people think that inflation had no predictions whatsoever. Well, but that's a debate that we can take off later on. But I think, this is a fact. You know, we've improved a lot. Now, what about curvature of the spectrum? Can we look at deviations? Well, not quite. Here is how much you can have a running of the spectral index of the primordial power spectrum. And this is what you would expect for, you know, typical single field monomial inflationary model. And, you know, we're not testing much there. We've checked something, but that's far from being enough. Now, let's just go one step further. Rather than saying, well, let's look at a power law, maybe with curvature. Let's just rebuild the primordial power spectrum. Because after all, this is linear physics, so we can invert. We can look at sort of everything that fits all the models of P of K, now the primordial spectrum, that fit the data. and then looks at all the variations in terms of cosmological parameters. So in effect, you are marginalizing of the cosmological parameters. So here is a result. That's actually the end of a fairly complicated process, because what we've done is a Bayesian reconstruction with varying number of nodes, sampling nodes in terms of k, and then each of them looking at the Bayesian evidence and then weighting all of them by this evidence to produce a final plot. And there is something that is of interest, I say, that I would comment. At L of around 20, you know that, well, it's been heavily commented that there is a dent in the spectrum in temperature, which is visually striking. Well, when you are trying to translate this into P of k, well, yes, there is something there. But you would, this is really pretty meager evidence. And so, yes, it's arresting. Yes, we've all been, looking at this, and there are other signs that there are bizarre things at large scales, but that's certainly not a strong evidence for feature or anomaly. And actually, we've done this like by 4 different methods, but I don't want to spend too much time on this. Now, of course, first, I hope that you've noticed that this is quite compatible with the scale invariant power law, that this is indeed not 1 just directly. And of course, we're losing it at very small scales because we have not a very large number of modes. We have a single universe. And at very small scale because there is noise and silk damping. So this is our window. And unfortunately, it's less than 10 E-fold. Well, too bad. The universe is providing with a window, but that's not a very large window. Okay, so still, I couldn't, what?
How are you supposed to read this diagram?
It's sort of, look at all, it's sort of, the color it gives you, according, the black is the most likely reconstruction. And then the further you go away, these are like 1 sigma variations. So you can sort of fit anything you want at sort of the 1 sigma there, at the 2 sigma. If you want, you could also think of this as you could sort of look at, well, do I have, let me.
But it again looks like it's sort of non-Gaussianity in the distribution of the modes.
Yes, it's not, it just says no, that you broaden, no, it means that the distribution function around that scale is much broader. It doesn't have to. Yes, it's broader. It doesn't have to be non-Gaussian.
Sorry, I didn't mean to say non-Gaussian, but...
yes, it's broader.
It's broader.
So yes, you can accept much larger deviation from the pure power law at that scale. Yes. Yes, it has to be shown somewhere that there is this lack of power. I'm just saying this is not tremendously significant. That's all what I'm saying.
And just say the non-Gaussian thing, but if you look at the centroid and the 1 sigma, that looks rather...
Yeah, I mean, it just says, I mean...
But then when you look at the 2 sigma...
Indeed. So it means that this is at the level of the 2 sigma each significance. Yes. May I suggest that we keep having these questions for the end? I'm supposed to cover 75 years in 25 minutes. I already burned 3 here. So, but I'd be happy to get back to any of those. Now, still, I mean, this is, by the type of exercise we're doing, we cannot look at any really fast wiggles there. There is just no way. So the only way that you can look at really wiggly stuff is to specify a model now. It cannot be a blind reconstruction. And of course, we've done that with a number of models with features, the potential, and so on, which marginally do better in terms of fitting the spectrum, in particular trying to fit the L of 20, which is there. But in the end, what we got convinced of is there is no model that is worth the extra cost you pay in terms of having more parameters. I mean, you are not improving enough the fit to the data given the number of parameters you are adding. So from the Bayesian sense, it's not really favored. Okay, let me continue on this. Well, another result that was also became pretty iconic is this famous plot. This has been discussed by many people with more cogently than I can possibly. The one thing I want to point out, of course, this is amount of primordial gravitational waves versus primordial tilt. And as we just discussed, I mean, you know, the NS equal 1, Harrison-Zeldovich spectrum is really, can be disproved at more than 5 sigma. This suggests this type of potential. The one thing that I want to put in perspective is how this fares versus direct detection, re-showing a plot that was shown yesterday, which is the sort of how we get with direct detections and as we are currently. And this is, well, with the constraint of the CMB, if you assume slow roll, that is to say, well, if you assume that there is no accident, that there is just a straight power law that as the small window we have allows, well, you know, this is, even in the very far future, this will not be, I mean, direct measurements will not be competing with CMB. But of course, that doesn't mean that this is worthless. I mean, this is not what I say, because it would be putting an infinite amount of trust in theorists. That is to say, well, you know, we have a theory that predicts no accident, so let's not check. That is not what I'm saying. But it's simply that, well, there might be a very long period of upper limits. That's all what I'm saying. There is something else that we've learned in the, this is a plot here that is actually, if you look at this, I mean, this is slightly better than what Planck alone does, because Planck is, of course, it's indirect. We don't have the possibility of doing a very precise direct measurement of the B mode spectra. So what we're constraining is the amount of tensorial mode that source the temperature power spectrum, right? But we can also add, I mean, after the analysis of BKP, which is, I mean, the bicep keg Planck, and well, you get there, so it's somewhat better. But what we've really learned as a community is that we have to be really careful about what dust does, in particular in the context of magnetic fields of our galaxy, which tends to provide a polarized dust background. So if you want to be really smart, you talk about polarized dust. I mean, that's even worse. And so, well, so that's one of the things we learned. Dust is in the way if we're trying to look at primordial gravitational waves. So I promise that I will talk a little bit about the future. So next steps. Well, we certainly want to improve constraints on running. Well, to improve constraints on running, we have to have a longer lever arm. Well, we cannot do this really with temperature. First of all, because we've extracted most of the information, and there is another part. We have all of these foregrounds which are picking up in temperature. You have point sources. Well, point sources are a huge contribution the further you go to small scales. Dust, CIB. I mean, this is really a complicated problem to deal with. But in polarization, the problem is much more benign from the foreground point of view. So if you master dust well enough, and this is easier in E mode than in B mode, then you can have, you know, you can think of maybe we'll be measuring things all the way to, say, maybe L of 5,000. Well, it's a lot more modes. And with a very tiny error bars, because, you know, the number of modes at a given L goes like L square. So, yes, we can do much better if we just, you know, well, build better experiments. Now, of course, we want to also improve the constraints or even better, detect a primordial stochastic background of gravitational waves. And well, typically, after lobbying all my colleagues that they stop talking about R, but they talk about sigma R, because this is really what we're trying to do. Because, you know, R doesn't mean, are you detecting it at 2 sigma, 3 sigma, 5 sigma? So just specify what is your sigma R you are shooting for. I think, you know, we are all thinking, well, with a lot of work, a lot of brilliant people working for a very long time, and a little bit of luck, we should be able to get down to sigma R of the FU of 10⁻⁴. In other words, if Starobinsky or Higgs inflation is around, we should be able to see it at more than 5 sigma. And of course, we should be able to do precision mapping if R is any larger, I mean, as was discussed. Now, that is a slightly different procedure because B modes tend to be, well, the primordial ones that are relatively large scale. And so But we have to deal with the fact that the very lensing that I mentioned to you earlier, the lensing that from which we're using the reconstruction of the dark matter, distribution integrated along the line of sight, that creates a foreground, if you want, which is E modes, which are being distorted into B mode, sorry, by the lensing along the line of sight. So one has to find a way to deal with this. And so that means that not only you need to measure the E modes very well, but you need to find a way of tracing the lensing potential. And there are several ways, depending on sensitivity and so on, that I cannot do in 25 minutes. There is just no way. That you can do it either internally or externally. Externally meaning that you might be using a tracer of it, which is correlated with the potential wells. And of course, if we get there, well, we'll also search for features of any kind. I'm not sure that we can get down to the level where we can read off, essentially the curvature of space-time directly from additional noise on the spectrum, but who knows. So to give you some idea of where you can dream, let me take some examples out of something I spent recently a lot of time on, which is this proposal, which, in its not so great wisdom, the ESA essentially science directorate and with their engineer declared that this was too expensive and that will not be doing it, even whatever the scientists say. Oh, Avast is telling me something that it's been, okay, well, deny. Oh shit. I really need to, I forgot to turn off the internet. So, well, that's, okay, so anyway, so let me take a few examples. I mean, that is not decided by any means. I mean, we are nowhere. But I think this is an example of what we can realistically dream of, just as I dreamed of Planck a few years back with a number of others. So let's look at power spectrum reconstruction. So this is sort of at the Planck level. That's the equivalent of what I showed you. And that's with a spec of core, what would be able to do in two cases, I mean, whether this is featureless or not. And so, well, you can sort of see that, the ability to look for wiggles, whatever, into the primordial power spectrum is amazingly enhanced. Because, of course, what you are doing is you are also refining, in particular, all of these cosmological parameters, which are not that interesting to do better, say omega b, whatever, but they allow you to compute very precisely what are the mapping, the linear mapping between, say inflation and the CMB. This is how we. So now these are the contours from Planck nowadays. Yet again in the NSR, and so these are two fiducial cases. Like I think that's a Starobinsky. Well, it's a sigma. It's an R of the order of 4 10 minus 3, and that's in the case where this is totally undetectable, which you can immediately see, and that was the other goal of this, is that we'd be able to exclude essentially all high field models of inflation, which would be not going after one model or another, but a full class. What about DNS over DLOC K? Well, that's a little bit tougher. Even core would increase the precision on running by not quite a factor of 3. This has already been commented, I think, by Renata, that decreasing the error on NS, well, by a factor of 3 is quite worthwhile, but this doesn't cut it yet to be able to really be very constraining and be to the guaranteed return, and that is guaranteed return, detecting it in a very generic case. So I just pull out this from a Porcido paper recently, that is a core light plus an SKA2, so we're really looking into the future, not even the SKA1, but SKA2. We would finally be in the regime where we could actually get direct measurement of the DNS DLOC K, that is the running of the spectrum. Okay, something else to dream about. Spatial curvature. Well, you all remember the old, there is the old degeneracy line of the CMB that goes, that's when we had the boomerang and maxima, the Jaffe paper and so on. So we started to see the fact that we were privileging and, something that was a region about that large, okay, because look at the axis. Now, just adding polarization, even though that this is not yet very precise, we're reducing the uncertainty in the degeneracy direction to this. When we add the internal lensing from Planck, I'm talking internal, no other data, just pure CMB, you get down to this blue one. And now once you check consistency with an external data set like BAO, well, this is what you get. This is what this number is coming from. Omega k equal 0 at the 5×10⁻³ level. Now, since we did that plot, there has been a new paper by Alam, which is having improved BAO. And now you get down, in standard lambda CDM, to the 2×10⁻³ level. Okay, so that's the kind of numbers we are in. And here again, look at how much progress we've made. This is, in a sense, the Melchior et al. Paper. We were at 0.4 error bars. And so, again, look at this. We've did a 100-fold improvement in about 15 years. Again, I mean, I think this is not bad, the rhythm of progress. Next. Well, I mean, from dynamics, I mean, we've proven already, I mean, that curvature is dynamically negligible. I mean, the impact on the expansion law is negligible at any redshift. So there is no motivation to go any further from the dynamical point of view. But of course, I mean, we know that, I mean, that a detection of departure would be tremendously important, well, for geometry, first of all. But this is also putting a constraint on, for instance, the type of inflaton potentials and so on. Generically, the level is at the 10⁻⁴ level. So I just told you we are at the level of, few times 10⁻�3. So there is. So can we actually make it? Well, here is a plot from these guys. So here, this is where we are now. With S4, which is a future ground experiment, plus LSST, plus SKA, well, we'll be able to do slightly better. Well, still not quite at the 10⁻⁴ level. So if we really dream how far we can go, there is sort of a curvature floor, which is at some point, well, how do you make the distinction when you have just at the very large scale between a very long wavelength mode from, say, inflation and, well, just geometry. And so I think there is still an interesting regime here that we can probe. I don't want to get into, well, not in the time I have all the details of the other parts. But I think we still have to invent how we'll be covering this decade there in deviation from 1 on omega k. No proposal has been made yet. Non-Gaussianity and anomalies. Yes, I know. Well, I'll do whatever I can. But give me 3 more minutes for all of these questions. So you know that there are a number of things at large scale that happen. I mentioned already the L/20 dent. There is a low multiple alignment that I'm sure you are aware. Statistical anisotropy, which is now I'm saying that the statistics of is slightly different in one hemisphere or the other. That's one of the thing that Planck found. But also, when we account for look elsewhere effect and all of that, none of this is really statistically decisive. So how can we do better? Well, this is at large scales. I mean, we're hit by the number of modes. In temperature, nobody will do better than Planck. That's it. So, well, if this has to do with primordial, I mean, with physics, we may hope, and this is coming from actually maybe the type of inflation and so on, well, then we may hope that this is going to be a sign in polarization. Well, polarization is coming. When I'm not speaking here, that's what we're trying to do, is to actually get to a map, not only a power spectrum, that you can trust at large scales. It's not guaranteed that we'll get to the point where we actually tell the community, yeah, use it, no problem, because that requires, I mean, being able to characterize residual, very low level of systematic that might otherwise be translated for, you know, signature that is confirming that we're seeing something also in polarization. Now you might say, well, okay, well, if you don't succeed, is this the end of the game? Well, yes, I know, it's 0. Can I finish my sentence?
It's not 0, it's less than 0.
Ah, he showed me 0. Sorry. Well, can I finish this transparency?
Yes.
Okay, fine. So I think it's not very likely that ground measurements will be able to help with those questions in polarization, because think of it, you have the ground pickup, you have to cover the 2 hemispheres and so on. We may have to wait for another satellite to get the CMB to help with that. Now, you might say, well, so what about other probes? Again, it's the only thing I can think of is SK type or intensity mapping type, but this is far from being demonstrated. Because, I mean, again, you would have to cover the full sky. That's really tough. And whether we can reach these kind of levels, I don't know. So I will conclude there. And there are discussions you can have on non-Gaussianity and a few other things. But I thank you.